Okay, so today I'm gonna I'm gonna use some PowerPoints to kind of give you again some very basic introduction about physics, kind of going along the line like we did yesterday, and then after that we'll go to chapter 1. Okay, so let me start from sharing the screen. Okay, and then let's go to the talk. Okay. You guys can see the talk, right? I mean, you guys can see the the slides, right? We're good.
Do you
Yeah.
post these slides on Blackboard?
Okay. So yeah, I want just make sure that we're not making the same mistake as we did like last time. So okay, so this is the physics talk we want to do here. Let's start from the very beginning. So for some reason, hold on, I lost my mouse. Let me. I want to move them to a place that okay. So let me do it again. Okay. So in this talk, I want to cover 3 basic questions. What is physics? Why do we care about physics? And how to do physics? Again, these are really fundamental questions that, but I think they're important to know at the beginning of this class. Okay. So what is physics? Now imagine this situation. Imagine you like in the summer, right, going to outside, you know, to a lake or to a pond, right? And then imagine you toss through a stone. You feel bored, right? So you pick up a stone and throw it into the water, right? And we can talk about physics of this process. So the first thing is we're doing physics is called observation. Okay, in this case, when you do something, right, like you're throwing a stone, you can observe the stone, right? Like it's a stone going out of your hand and then going back to the water. Well, I have some like maybe let me change it to wait. Let me change to no virtual background. Okay. So see, for example, I have this ball here, right? Like the same, it's the same thing as I throw a stone, right? If you throw this thing, right, it's gonna go like this, right? It's gonna what's gonna observe something like this. So if I throw it again, maybe another stone, right? Again, you'll see something like this, more or less, right? Now, based on this, what can you observe? What can you conclude? What is the something common when you throw a bunch of things, you know, like this?
It goes down.
It goes down, right? Yeah. This is something really simple, right? But certainly whatever you threw, right? And whatever it looks like, but eventually it's gonna goes down, coming back to the ground. Okay. So so that's you got this by observing it, you know, observing things. And so based on your observation, you could come up with some idea. Sometimes they're called hypotheses. In this case, the simple idea you can get is whatever you threw into the air is going to go back down to the ground. Okay, so that's the idea, or you can say this hypothesis. You may feel, okay, this may be true for not only the stones you threw away, but for anything, you know, for other things as well. So how do we verify this idea? Okay, now the next step is to do an experiment. Okay, so what we want to do is, based on our observation, based on the idea coming out of the observation, we will try to do a experiment, try to verify this idea, verify to see whether it works. So when you do experiment, is a little bit different from the observation, because in this case, you actually put everything in a very well controlled situation. Like you go to a lab, you know, make sure everything is set up carefully, and then you can repeat it under same conditions, you know, like for different kind of specific things, and you can take measurement. Okay. Now let's say, suppose you did this bunch of experiment by throwing other things or whatever things you want to the air, and you can verify they all go back to the ground, right? And then to verify this even further, you could do this experiment at different time of the day, and then at different locations. For example, you can do it at home or do it at work, do it like outside, do it in Tulsa, do it in other places, et cetera, right? After all that, we could come with a law of something we call law of nature. In this case, it's simply like everything out in the air will come out to the ground. Okay, let me hold on. Let me see this. Okay, yeah, everything throughout in the air falls, right? And then so this is basically the 4 steps, kind of critical steps that we take when we're doing physics. In general, that's the steps we take when we do science. Okay. Now the critical step here is actually the experiment step. That step is actually essential. Okay, and that separates science from everything else. And that's why we need to have our lab component in this class, because without that, we wouldn't be able to get anything. So everything we learn from lectures, everything you see from the textbook come from essentially the experiments, okay? Again, if you have any questions, let me know. You can send me a message, but actually it's even better if you can just talk to me directly, you know? I mean, we don't have many people here, so it's like a small class, you know, we can just relax and just chat, you know? And this is the advantage you take by showing up in this virtual lecture. You know, we can talk to each other directly. If you have any questions, the best way to get the answer is just ask me, you know. It's better than you going to textbook or to wherever, you know, to find out the answer. So anytime you have a question, don't hesitate, just ask me, okay? Okay, so let's do a specific kind of, I mean, let's talk about this specific example. That's kind of going along the same line as you threw something in the air. Okay, this is called the free fall problem. Okay, now this problem is, so if you have a tennis ball and a baseball, okay, you see, certainly, do we have any question here? Okay, so let's say, I mean, as we know, right, the baseball is heavier than the tennis ball. They have a similar size, you know, but the baseball is way heavier than tennis ball. Okay, the question is, if you release them at the same time from the same height, which ball falls to the ground first? Okay, now in my case, I have this table here. So say same height from same time. Which ball falls to the ground first? So what do you guys think?
Baseball.
Again, go ahead.
The baseball, it weighs more.
Baseball, okay. Anybody else?
It'll fall at the same rate.
Why?
Because weight doesn't determine how fast something falls through gravity.
Okay.
Or gravity affects it. It doesn't affect the weight any different, is what I'm trying to say.
Okay. Okay.
Like gravity doesn't affect it any differently.
Okay. Anybody else? Anybody think the tennis ball would fall to the ground first? Okay. So now we have this question, right? Now we got different answers. What should we do? How should we figure out which answer is correct?
Test it.
Right, exactly. So this is what we just talked about, right? Just doing the experiment, right? So let's do this. Okay. Again, we don't have really fancy equipment in here, but let's just use our eyes. You know, see same height. Okay. So what do you think? Okay, I'm gonna drop them from a higher height, but still same height. Okay. What do you guys think? Maybe, I mean, based on your hearing, you know, like the sound, and also like which one falls ground first? Can you tell, or is it too hard? No?
They sound the same to me. They sound pretty similar.
Yeah, okay. At least for our simple experiment, right? It sounds like they fall ground at the same time. Now you can do this easily at home with something like this, you know. you can try, take two things with similar size, but different weight, try to drop them same height. Okay, it turns out that if you do it really carefully, it turns out they will fall to the ground same time. But actually, this is not a trivial fact, okay? Actually, for a long time, people thought that the heavy object would fall to the ground first. And that was one person that kind of promoted this idea was Aristotle. He lived in ancient Greece, as you see here, like about 300 years BC, okay? So he thinks the heavy object falls first. Well, after him, because he's so great, people all kind of believed him, they all thought that the heavy object should fall to the ground first. Until really recent, we got another guy, Galileo Galilei. He lives in Italy, and then in like 16th century. He thought, he didn't agree with Aristotle. He thought that these two should fall to the ground at the same time, okay? Well, this is not a trivial idea, right? Because it seems like, if you just think about it, right, it seems like the heavy thing should go first, right? Because bigger force, right? Now, so who is correct, right? And Galileo Galilei was now he didn't just stop claiming that, but he went ahead, did an experiment, okay? So the story said that he climbed all the way up to the top of the Leaning Tower of Pisa. And then at the top of it, he had two balls with him, okay? With exactly same size, okay? One of them is 10 times heavier than the other, okay? And then he dropped them by himself at the same time. And then and a lot of people was actually observing it together. They all see that these two balls hit the ground at the same time, okay? So that was pretty amazing, okay? Now, again, what I want to emphasize here is it doesn't really matter whether your idea is wrong or right, okay? What matters is whether you have a way to kind of verify it, okay? To test it, okay? And that is based on our, what we learned today is you have to do an experiment, okay? That's a very simple idea, but that idea was really, really powerful. Actually, Galileo Galilei was considered as the founding father, one of the founding fathers of modern science, not only because he got a lot of great things, but basically because he kind of set up this scientific method that we just talked about, the 4 steps, and then most importantly, using experiments to verify things, So, so that's that, okay? So actually, let's go a little step further, okay? Let's follow what Galileo thought about, okay? Why did he think about they should go to the fall to the ground at the same time? It's a really smart argument. It does not involve anything complicated or any sophisticated theory. But so I like to share this argument with you guys, okay? So his argument is the following, okay? So take the tennis ball and the baseball, right? Now, suppose Aristotle was correct. Suppose the heavy object falls faster. So then we would say that the baseball falls faster than the tennis ball, right? Now, Galileo said, okay, let's connect them by a string, okay? Okay, now, after you connect them, how fast this whole thing fall compared with either the tennis ball or the baseball, right? Then people can say this, okay, because you connect them together, they're heavier, right, than either the baseball or tennis ball. So based on the same argument, the whole thing should fall faster, right? Because it's heavier, right? If Aristotle was right. However, from another point of view, okay, if you say the baseball is falling faster than tennis ball, after you connect them, right, you drop them, what's going to happen? What's going to happen is the baseball is going to go faster than a tennis ball, right? So the baseball try to go down, but the tennis ball moving slower. So the tennis ball is going to drag the baseball. So the whole thing is going to fall slower than the baseball, although it's going to fall faster than the tennis ball. But seems like they're going to fall kind of in the rate that's in the middle. Okay, so they should fall slower than the baseball because the tennis ball is kind of dragging it back. Okay? But this gives you a contradiction, right? Because based on the same argument, Aristotle's argument is heavier, so they should go faster. So from there, Galileo think that, okay, there might be something wrong. Maybe this idea, this hypothesis that heavy object goes faster is wrong, okay? And then at that point, he decided to do the experiment. So I think this idea, I mean, this kind of argument, by setting it up, is really smart, okay? But see, doesn't matter how smart it is. In the end of the day, you have to test your idea by doing an experiment, okay? Without the experiment, your idea can still be wrong, okay? Does that make sense to you guys? Okay. Do you guys like this idea? I mean, I think this is really smart, okay? Anyway, so he got a contradiction as we said, okay? Now, let me ask you this following question. Can you give a counter example? Like when you drop two things, one of them goes way faster than the other one?
Say a
What about-
rock or a feather.
Oh, yeah. Okay, Hannah, right? What do you say?
A rock or a feather.
A rock and feather, right? Okay, good. Nathan, or your name Nathan, or is Nathaniel?
Nathaniel.
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 I'm sorry, Nathaniel. Did you
No,
say
you're good.
something as well?
I was going to bring up a feather as well.
Yeah. Okay, good. Okay, certainly that's. I mean, I don't have a feather with me, but I have something else. I can show you the similar thing. Okay, so let's take a baseball and a piece of paper, right? Well, you can drop them. Without doing this, you probably already know the answer. So if I drop them same height, certainly the baseball go faster, right? Doesn't matter which height I use. Okay, because it's like this is going to be so slow. So now, see, that's how science progress, right? So you got some laws, it applies to some cases, but you would always think about some counter examples. Okay, you would think about when at which case the law will not does not apply. Okay, well, we found an counter example, right? So why in this case it does not work? The law we just discussed not working. Well, what is the new factor that we didn't talk about?
Surface area.
Okay. Surface. Yeah. But essentially, it is because the air resistance, right? See, there's air, and then this has a much bigger surface, so it has bigger air resistance. Okay. So it slows things down, and that's why before we talk about this experiment, we're kind of saying that okay, we have used basically same kind of roughly same size objects, you know, to do the experiment. Otherwise, if you have one case which is way bigger, like when you have an object with really small mass but very large surface, then what we just discussed did not work. Okay? Now you can check whether this idea is correct, whether it is indeed the surface area that or the air resistance that give you this. Okay, so how do we check? Okay, there's a way to check. Okay, so take two pieces of paper. Okay. Say two pieces of paper, right? Now, crumble one of them. Well, by doing that, I'm not changing any mass, right? The same, they have identical mass, right? But then when you drop them, certainly you see that this one goes way faster. And it's pretty obvious, right? This one's gonna go way faster. Well, again, this kind of verifies the idea that the surface area is the thing, or the air resistance is the thing, because they're obviously same objects. The only difference is you reduce the area of this one, you know, by making them like this, right? So we conclude that air resistance is important, okay, sometimes, okay? Especially when you have cases that when you have a really large surface area, right? So again, I cannot see my own. Okay. So now next question we could ask here is, now suppose this is correct. Let's say it is the case that the air resistance kind of stopped and slow down something, you know, kind of make our experiment not accurate. Then to verify, you could think about another situation, right? What if we can do this experiment in the place with no air? In that case, we can see that like they fall to the ground at the same time, then it's verified, right? So actually, this experiment has been done, okay? I mean, not only once, but you go to YouTube, there's a bunch of cases you can see. But let's go to one case, okay? So actually, this feather and hammer experiment has been done on the moon by Apollo 15. So let's do that one, okay? Let me show you this video.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his findings.
Okay. Yeah, I think that's pretty amazing. I like this a lot, you know. Wait.
Knock, knock.
No,
Hello?
I just stop this. Okay. Yeah, it's very, very kind of very cool, you know. Like you go to the moon and you do this simple experiment, but because, as we know, because there's almost no air on the moon, the reason for that is air has the moon has a way smaller gravitational field, so it cannot hold the air around it. So there's almost no air. So you can do this experiment there, and then you see that amazingly the feather and the hammer will just fall at same rate, same time. So Galileo was right, you know. And the second part we talked about was it is indeed from the air. So what we can conclude about this, the summary of this free fall motions, we got a couple of things, okay? Without air resistance, all objects fall with the same speed and acceleration, okay? So they reach the ground at the same time, okay? Now, why is that? Okay, we didn't talk about this here, but essentially due to Newton's law of universal gravitational attraction, we'll learn that later on in this semester. But for now, we have to just take this statement. But it is not so important of exactly why, and I mean, for the specific case, what kind of thing we learn. I mean, but what I want to show you is a whole procedure, how physics works, you know, how science works, you know. See, at the very beginning, we had some observation. We got a question, we did an experiment, and then we got some idea, and then we kind of deepen our understanding by thinking about some counterexamples, and then think about other cases, and then we try to verify each one of them by doing further experiments. And then we also ask questions of why, and then try to get even more idea or understanding of nature. That's how physics goes. Okay.
I have a question.
Go ahead.
So in the equation for gravitational force, it includes mass. So with that being said, why does the tennis ball and baseball fall at the same speed?
Yeah, the reason for that is the force itself is proportional to the mass, but then force equal to mass times the acceleration. So the two mass kind of cancel out. So the acceleration actually end up is independent of mass. Okay. Again, it's like we haven't learned this yet, so we'll learn this about it later. Does that answer the question?
Yes, thank you.
Okay. Good. So basically, I want to summarize about what is physics. Okay. So basically, physics studies nature, or you can also call it the world or universe around us. You know, and and experiment is the most important thing in doing physics or science in general, because all the knowledge we have come from experiment, okay? And thinking and using logic is also kind of very important. Without being able to think, see, in the whole process as we just discussed, right? We need to think, we need to ask questions, we need to figure out some reasonable answers for that, right? And then we use experiment to check our answer. So think is also important, okay? So let me talk about a little bit a couple other branches in natural science, kind of build out, set up kind of the big picture here. So physics is kind of like the fundamental level about nature. So you want to ask questions about nature, try to understand nature. If you keep asking this question, why and why and why, eventually you'll go to physics. Okay, physics give you the most fundamental possible understanding for nature, and then above physics you can build on chemistry. For example, as we know, like all kind of chemical reactions stuff. Essentially, those chemical reactions are determined by the chemical compounds structure, their properties, and those properties are determined essentially by the structure, atomic structures of those molecules, and then those are determined by quantum mechanics. So this is how chemistry can be traced back to physics. Now, similarly, we have astronomy, which is tightly related to physics, like how the planets rotate around on the sun, and then the galaxies, you know, and then black hole, supernova, all these kind of phenomena. Eventually, we need to use physics, specifically Einstein theory of relativity, to explain it. Well, Newton had the universal gravitational attraction. That's also useful to explain what's going on in astronomy. Okay, so if you go in astronomy, go deep down, you got physics as well. Okay, now there's also like earth science, you know, how the structure, how the earth is formed, and then how the continents are formed, and the mountains, the ocean, river, etc. These essentially can be traced back to physics as well. Well, biology is a little bit higher level because it's deal with even more complicated system. In the single cell, a simple cell, there's a lot of like stuff in it, and then there's all kind of biochemical reactions happening, and then essentially all of this can be traced back down to physics as well, but it's a higher level, right? Well, what about mathematics? It turns out mathematics is not a science by itself, in the sense that you do not need to do experiments in mathematics. So as far as you can do logic thinking, you have mathematics. You can start from something called axioms, like some of the mathematics you guys know, and then you can derive all the theorems starting from the axioms. You do not need to worry about whether the axioms are real or not, you know. But we do need, physics do need a lot of math here, okay? Well, this picture I'm showing you is maybe to a little math. But as you can see here, right, there's all kinds of formulas we use, you know. I mean, there are mathematical formulas. We use symbols to represent like the physical quantities, and then we find the relations using math. So math is actually very essential for physics. And for this class, we need algebra a lot, meaning we need to work with symbols, okay? Because that's the very convenient way to write down your mathematical equations. So, yeah, so that's very important for us, okay? So why do we care about physics, okay? Well, there's all kinds of reasons, but certainly this is the first reason. It's a required course for a degree, right? So without taking that course, you won't be able to get your degree. So, and why not, right? If you're just curious, you know, you're interested in the nature, you know, you probably at night you go out to look at the sky, you know, look, when you see the stars, you will start to wonder, what are they, right? How far they are from us, right? How big is the universe, right? I mean, I think this is a pretty natural, you know, like we are all curious. I know you guys, I mean, when we grow older and older, we're not as curious as we were before. But I think it's still like, I mean, for physics, I mean, we should have our curiosity. If we have the curiosity, we should be learning physics, okay? And then the physics also can help us to build our world view to the world we're living in, okay? We see the world actually can be simplified, can be understood as a bunch of mathematical laws. The world has some orders, you know, it's not totally chaotic, you know. So I think it's useful in this sense, okay? And then certainly physics and other science lead to technology, which is critical for our modern civilization, right? See the technology we're using right now, the internet, right? Coming from essentially computers, while the computers coming from essentially the semiconductor physics, this integrated circuits board, right? And then the semiconductor physics coming essentially from quantum mechanics. So it's all kind of built up one after another. So the point is for you guys, right? For a lot of you guys, this is probably your first class in physics and might be the only class because a lot of you guys have health majors in health professions or math. You guys may not be able to use physics directly, but I think it's going to help you to develop your critical thinking ability, like how to solve a problem, you know, how to think, how to figure things out. So I'm going to try to emphasize those things in our course to help, because I know you guys are not going to be physicists anyway. So otherwise you'll be majoring in physics. But I think still like this is important to learn about it, you know. Now the last question: how do we do physics, right? So certainly, the first thing is you have to listen to your physics professor, right? Like me in this case. So as far as you listen to what I said, you know, if you follow what I said, you'll be good, okay? Now, I also want you to be able to think, you know. So keep a reasonable doubt about everything. Always ask why, you know. Don't just take something for granted. Even if it's in a book or coming, I mean, from me, don't just think, okay, because he's a physics professor, he must saying everything right. Not necessary, you know. Everybody makes mistakes, and everybody, I mean, if you're not careful, you could say something stupid easily, you know. So keep thinking about yourself, okay? Also, try to understand instead of memorize things, okay? Now, I know for a lot of you guys majoring in health professions like biologies, when you study a course, probably you need to memorize a lot, like the names of different proteins, different enzymes, et cetera, right? But in physics, in this class, I do not want you to do that. I do not want you to memorize things. I want you to try to understand it, try to use your brain to figure things out. Okay? Now, to encourage this, I'm not gonna require you to remember the formulas we learned. In the test, I'm gonna give you the formulas. So there's gonna be a formula sheet, and then you can use the formulas from that sheet to do the problems. So just try to focus on how to use the formula, right? How to solve the problem. That's the most important thing. Okay? And I think this is especially important in our information age. Now, if you have something vague, you want to know what it is, it's very easy to search it online, to get an answer online. And but to be able to use the information online, you need to be able to understand. You need to be able to think, right? So I think thinking and understanding is more important. Okay, now another thing is you do need to solve problem with math, and then we'll have a homework problems for you guys, and problem solving is actually very important part of this class. I'm going to talk about specifically what do you do to solve problems when we get to there, okay, when we get to chapter 2, okay. So basically, there's a couple of things I think specifically may help you in this class. First of all, lecture and notes. You need to come to lecture, take notes. Again, I think the come to lecture specific at this time is better than just to look at the video, because you got to ask me questions. and also do your homework on time, and then try to read textbook. Okay, the textbook is pretty long, so you may not have time to read all of it, but try to read something that relate to what we talk about. Okay, or I know some of you guys prefer to watch videos, learn from videos. Just go to YouTube, you know, Google like the search the keywords, and there's a bunch of nice YouTube videos on physics as well. Okay, now another one is like try to ask questions. Okay, again, as I said, right, it's important to be able to think, and asking questions is just like one specific way of thinking, you know, and that's a very important way of thinking. So try to ask questions. Okay, and the last one here is try to form a study group. I know it's kind of hard for this specific class because we're all kind of online, everybody's by yourself. But I think if you can, try to, if you have some friends in this class, try to form a study group, you know, try to work together on your homework. I know probably it's not, they do, probably we're not supposed to get together a lot because of social distancing, but you can get together like online, you know, like through Zoom meetings. The study group is gonna be, it's gonna make it way easier for you, you know, for when you learn something really hard. Okay. So finally, let's talk about what is the study physics look like, feels like. Okay. Now there's two possibilities. One is like this. Okay, it's like you go to the beach, you know, you enjoy relaxing, enjoy the sunshine. And the other one is this. Okay, you're climbing a mountain. You know, let's say it's Mount Everest. Okay, you're climbing it up, and it's outside it's cold, it's windy, you know, not much air, and you're really tired, you know, but you still need to go to the summit of the mountain. So what do you guys think? Which one is will be more like in this class? Which one do you expect it to be?
The mountains.
Yeah. I think the real experience is probably neither of them. But if I have to choose one, it's probably a little bit closer to climbing the mountains, you know. But I mean, it may not be that hard, you know. Again, it really depends on how much effort you put in. The more effort you put in, the easier it's gonna be. And so finally, let me say this, okay? Physics is not easy, okay? But it's enjoyable, okay? I don't know whether you guys have this experience, you know, like you're trying to work on some problem, like a math problem, something, and it's really hard. You just cannot figure it out, but you didn't give up. You keep doing it. And then until one day or one time, you know, one moment, and suddenly it clicks, you know, suddenly you figure it out, you know. And at that moment, you feel really happy, you know. You feel like you got something. You feel like you learned something new. You feel like this is something different, you know, just it's not something you know before, you know. That's kind of feeling, you know, is why physics is enjoyable, right? Again, it's not easy. It's definitely not easy, but it is enjoyable. And if you really think about anything in your life that's valuable, it's not easy, right? Nothing is, if you like just easy, like say you just lay on your bed and then you enjoy, and then suddenly something good happened, right? But it's not like, it doesn't work like that. Anything valuable in your life, whether it's a fitness class or a decent job or a long-term relationship or a